In this video, we are going to look at merge sort. After looking to simple sorting algorithm, bubble sort and insertion sort, now we are going to look at merge sort, which is considered more advanced in comparison to, say, bubble sort and insertion sort. And as you will see at the end, it is significantly more efficient uh, than those two algorithms as well. Now, the idea of merge sort, to explain that, let me briefly talk about a paradigm in uh, designing algorithms, which is called divide and conquer. Now, in a course that is dedicated to algorithms, there will be multiple lectures talking about this paradigm. But for us here, I'm going to just remind you that this is something that we did in binary search as well. And the idea is very simple. You have an input that you want to do some kind of input computation on it. And what you do is, instead of directly working on the input, you divide that into smaller instances of the same problem, or as we call them sometimes sub-problems. And then you solve each sub-problem individually and separately, usually by using recursion. And then at the end, when you have the solution to each sub-problem, you combine them together to construct the solution to the original problem. So divide, conquer, and then combine. Now, as I said, binary search, which we saw before in previous uh, previous video, binary search is based on this idea of divide and conquer. Because if you remember, we had an array of elements that are sorted, and then we had a target that we wanted to see whether or not it happens anywhere in the array, and if it does, where, at what position. Now, the way that we did it was we looked at the element in the middle of the array, target and x, and if they're equal, then we are done. We say we found it at this index, whatever the index of the middle position is, and that's the base case. But if not, then it's either the target is less than x or greater than x. If it's less than x, because we assume that the array is sorted, if target is less than x, then we only need to search the first half of the array, right? So immediately you see that we divided the array of size n into a smaller array of size n over 2, and we are doing our search on that half. So divide and conquer. And on the other hand, if target happens to be greater than x, then because again the array is sorted, uh, we only need to look for the target in the second half. Again, an array of size roughly n over 2. So divide and conquer. That was the basis of binary search. And as we will see in this video, it will be the basis for um, a merge sort as well. Okay. Now, I will start by explaining how merge sort works on a very high level, and then gradually make it more concrete. Okay. So here's the explanation using a picture. So we have this array of size n. Okay. So size is n, and it's not sorted. And we want to apply merge sort to this array to sort it. So the first thing that merge sort does is that it divides the array exactly in the middle into two halves. Okay, so two subarrays, each one of them has size roughly n over 2. I say roughly because it could be that n is odd, but that's a small detail that we're going to ignore at the moment. So size is n over 2, and still not sorted because the only thing that we did was we divided the array right in the middle, right? So size is n over 2 here as well, and not sorted. Okay, and I'm going to call this subarray left and this one right. So that's the divide part, right? Remember divide and conquer, right? So now we did the divide part. Now for conquer, what we do is separately we sort each half, and we do that by making recursive calls to merge sort again. We call merge sort on each half recursively, and what happens is you get two arrays of the same size n over 2, The size is n over 2 again for both of them. Size is n over 2. And the elements here are going to be exactly the elements in the left half, except that they are rearranged, so now they are sorted. Okay, so for that reason, I'm going to call this left prime. And the elements here are going to be exactly the elements in the right half, but now they are sorted. So I'm going to call this right prime, rearranged. Okay, so now we have the first half of the original array sorted, and the second half of the original array also sorted. But if you think about it, we cannot just put these two together and say, here you go, this is the sorted array, because it could be that this left is like 1, 7, 10, it is sorted, and then this one is 2, 8, 15. If you put them together side by side, even though both of them are sorted, the result is not going to be sorted. So it requires a little bit more work. And as we will see, that extra work is going to be called merge, hence the name merge sort. And merge takes two subarrays that each one of them is individually sorted, and then merges them into an array of size n that is sorted. And then we are done. So here size is back to n again, and it is sorted. So the elements here are going to be exactly the elements in the original array, except that now they are sorted. So this is the picture of a very high level description of how merge sort works. But at the moment, it probably seems like magic how actually sorting happens in this process. And as I said, gradually we are going to build our way into the details of this. So for the next step, what I'm going to do is I'm going to show you how this process works on a small example. Okay, and let's say an example of size 4. So here's my example. Let's say the original array has size 4, and it's an array of integers. And for the values, let's say we have 7, 3, 5, and 4. And we want to apply that algorithm to this array. So step 1, the first thing that merge sort algorithm does is divide into 2 halves. Okay, so the first half will be 7 and 3. The second half will be 5 and 4. Then, if you look at this picture here, after divide, we call merge sort on each half. Now here, I did that immediately, but really what happens, if you want to go into details, when I call merge sort on this array of size 2, remember the first thing that merge sort does is it divides the array into 2 halves. So when I recursively call merge sort here, it divides this array into 2 halves again. So we get 7 and we get 3. Similarly here, when I call merge sort on the right half, the first thing that merge sort does is divides that into 2 halves, so 5 and 4. Okay, so and now again we call merge sort on this array, this array, this. So 4 recursive calls, 2 for here and 2 for here, merge sort. Now, since merge sort is a recursive function, we definitely need a base case, and the base case is exactly here. When the size is 1, when you call merge sort on an array of size 1, it can just return the array as is, right? When I call merge sort, it just returns 7. When I call merge sort here, it just returns 3. When I call merge sort on this array of size 1, it just returns 5, and this one just returns 4. So these are all merge sort recursive calls, right? That's the base case, because an array of size 1, no matter what the element in the array is by default, by definition, is already sorted. Now we need to merge them, right? Remember, after the recursive calls return, we need to merge them. And if you merge 7 and 3, we get 3 and 7. I haven't told you how merge works, but for arrays of size 1, it's kind of trivial. So let me explain it in the next step. So merge, this becomes 4 and 5. Okay, so now we have this first half sorted, 3 and 7, the second half sorted, And remember, when we get back the result of merge sort, left and right sorted, we need to merge them again. So these two halves need to be merged for the final time. Okay, and this is a good place to tell you how the merge subroutine works. So here we had merge, merge, and now the final merge. Okay, now here's how merge works. First of all, the merge subroutine, we are going to talk about this in detail through another example, focusing only on merge. And also when we are talking about implementation, we are going to go into much more detail about how merge works. But for now, let's think about uh, how merge is going to work. So the first thing is that merge is taking two arrays and it assumes that each one of them is by itself sorted. So 3 and 7, that's sorted. 4 and 5 also sorted. So that's the assumption. And now it has to merge them into one sorted array. Now, the way to do that is, in the first step, we only need to look at the first element here and the first element here, because the smallest value in the left half is the first element because it is sorted, and the smallest value in the second half is also the first element because the second half is also sorted by itself. So the smallest element overall is going to be between the first element here and the first element here, whichever is smaller, which happens to be 3. So we write that 3 in the final answer, and now we can get rid of 2. And repeat. Now the smallest element in the first half is the new first element, which is 7, and the smallest element in the second half is the first element, 4. Between 4 and 7, 4 is smaller, so we write 4 here, and then get rid of 4. Again, we have 7 and 5. 5 is the smallest on the right side, 7 is the smallest on the left side. Between 5 and 7, 5 is the smaller one. The 5 goes here. And then eventually one of the two halves is going to be finished. And then what we do is we copy what's left in the other half. So here we have it. 3, 4, 5, 7 is exactly the same numbers that we had on the top, but now they are sorted. So that's roughly how merge sort works. But this, and as you can see, is nothing but divide, 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 divide until you reach the base case. The base case returns the array as is because it has size 1, it's already sorted. Then most of the rearranging happens in the merge function. And that will show when we talk about the implementation as well, because as you will see in the next video, when we talk about implementation, the merge function itself is a few lines of code. Finding the middle index and then making recursive calls, and then at the end calling this subroutine merge. Most of the work will be done in the merge function. Okay, so because of that, I want to focus on merge itself a little bit more, so that when we talk about implementation, it makes more sense. Okay, so here's my example for merge sort. Um, I'm sorry, for merge only, focusing on it a little bit more. So here we go. Here's another example, only on merge. Okay, so let's say we have two arrays, this time of size 4 to make it a little bit more interesting. And each one of them is sorted on its own. We want to merge them into one array of size 8 that is sorted. So let's say the first array is 2, 7, 15, 21. And the second array is 4, 8, 10, 13. And we want to merge them into an array of size 8. That is sorted entirely. Okay, now I can go through the motions as I described there. So 2 and 4, 2 is the smallest on the left side, 4 is the smallest on the right side because the left side is sorted by itself, the right side is sorted. So between 2 and 4, the smaller value is 2. But then remember I said that to get rid of 2. But if you're implementing this in C++ and these are arrays, in getting rid of an element, you cannot delete an element from an array in C++. So I want to be a little bit more precise in my terminology now because we want to get closer to the implementation. So instead of saying get rid of it when you copy that element down here, we can have a pointer or an index that starts at the beginning, and then when we are done with this 2, we move that pointer or index to the next one, and then when we are done with 4, we move it to the next one, and so on, right? So I'm going to have a left index. I'm going to call this just left. So we have a left index that originally it says 0, and then a right index, or if you're more comfortable with pointers, you can use pointers as well. That is original 0. And then I have a result index that is also 0 for copying. Okay, now I compare these two, 2 and 4. So, and then since 2 is smaller than 4, I copy 2 here. And then instead of getting rid of this, I increment left. So left becomes 1. Okay, and now since this position is occupied, I need to move right to the next position as well. You get the idea, right? Now we compare what's on the left side at index 1, which is 7, and what's here at index 0, 4. 4 is smaller, so we copy 4 down here. And then, since we are done with this, we move right to the next position. So right is equal to 1, and also result. This should be result, not right. Result should move to the next position as well. The result is now 2. Okay, again, compare what's here at index left, which is 7 and 8. 7 is smaller, so we copy 7 here, and then we move this guy, left index, to the next one. Compare what's here at index right, which is 8 and 15. 8 is smaller, and then result obviously goes to the next one. So you get the idea, right? So instead of saying get rid of 2, 7, and so on, we have this pointer or this index that goes up every time that we select something from either left or right to copy here. And no matter from which array we select that, the result index should go up every time because we write something, it should go to the next position and the next position. So let me not go through this whole motion, or let's do it. So now result, let me erase, made a mess here. So now result is here. The result is 4. Okay, and since we copied right, right is also 2. So right is equal to 2. So now we are comparing 15 and 10. 10 is smaller, so we write it here. Now right becomes 3. And result also should go forward. The result is 5. Here, right? Now we are comparing 15 and 13. 13 is smaller, so we copy it down here. Result right should go up. So the right becomes 4, which is out of range. Okay, and result should go up again because we copied one element down in the result array. So result is 6 now, looking at this location. And now, since one of the arrays is completely done because the index is out of range for this array, what we need to do is we just need to copy whatever is left in the other array down here. We don't need to make any comparisons because each array by itself is sorted. So if one of the arrays is done and you have 2, 5, 10 elements left in the other one, you just copy them down in the same order. So 15 and 21, and we are done. Okay, so in this picture, we talked about erasing the elements when we copy them, but a more accurate way of saying that is you can have pointers or indices that go forward whenever you copy an element from either left or right, And then there's another index or pointer for the result array that goes down and goes forward by one every time that you copy either from the left or from the right side. Okay, so that's the idea. And in the next video, we are going to look at how we can actually implement this.